Welcome to this explainer. Today, we're diving into a really fascinating lesson from the Smart Academy that blends geometry and algebra with concepts of godly order. We're going to be looking at how they connect the hidden structures of our physical space to mathematical theorems.
Here's our roadmap for today. We'll start with the geometry of truth, move on to unlocking the theorem itself, solve some real-world distances, plot diagonals on a grid, throw a quick homework challenge your way, and finally explore how this curriculum ties education and math back to morality.
All right, Part 1, the geometry of truth.
The source material actually anchors its teaching in Psalm 25:4, which says, "Show me your ways, Lord, teach me your paths." The curriculum uses the scripture to argue that learning is really about seeking out divine structure rather than just settling for chaos. It kind of frames math as a way to seek out the dependable rules that hold our physical and spiritual reality together.
And this perfectly highlights the curriculum's main point, the stark contrast between the chaos of just eyeballing things and the peace of true precision. I mean, think about it. Whether you're designing ramps, flying drones across an open field, or trying to measure from corner to corner in a local park, using right triangles lets you totally abandon guesswork. You rely entirely on structured math. You aren't just hoping you measured it right, you know it for a fact.
Moving on to Section 2, Unlocking the Theorem.
So, let's meet the famous formula that brings all this structure to right triangles. The absolutely crucial thing to remember here is that this dependable little formula only works for right triangles. It connects geometry and algebra using one incredibly simple equation: a squared plus b squared equals c squared. This lets you solve for the shorter legs, those are your a's and b's, or the longest side, which is called the hypotenuse, c. Basically, whenever you see a right triangle, this formula is your master key.
Finding that hypotenuse is a super logical three-step process. First, you square the length of each leg. Second, add those two results together. And third, just take the square root of that sum to find your total distance. It is elegant, it's repeatable, and honestly, it works every single time.
Section 3, Solving Real-World Distances.
Let's see how this actually applies in the real world. Imagine you're out for a walk. You walk exactly 6 feet east, and then you turn a sharp 90 degrees and walk 8 feet north. Now, how far are you from your starting point if you drew a straight diagonal line? Well, applying our theorem, we just square our legs. 6 squared is 36. 8 squared is 64. 36 plus 64 equals a nice neat 100. Then, take the square root of 100, and that gives us our exact diagonal distance.
Which is exactly 10 feet. You are precisely 10 feet from where you started. No tape measure required, no eyeballing, just pure, structured truth.
Now, what's really interesting is how this formula can actually work in reverse. Because, we don't always need to find the longest side. What if life gives you the total distance, but you're missing a piece of the journey, like a missing leg?
For example, if our longest side, the hypotenuse, is 13, and one of our legs is 5, we just set it up the exact same way. A squared plus 5 squared equals 13 squared. That becomes a squared plus 25 equals 169. By subtracting the squared leg from the squared hypotenuse, meaning 169 minus 25, we get 144. Then, you simply take the square root of 144, and you find that the missing leg is exactly 12. It's a perfectly balanced equation.
All right, Section 4, Diagonals on a Grid. Sometimes distances aren't walked. They're plotted on a map or a blueprint. So for our third example, we want to find the exact straight-line distance between two specific points on a grid. Point A is at coordinates 1, 2, and point B is at coordinates 7, 5. To figure this out, we have to uncover the invisible right triangle hiding right there between these two dots.
We find that hidden triangle by calculating the change in our coordinates. Look at the change in our x-axis. Moving from 1 to 7 means our change is 6. And for the y-axis, moving from 2 to 5, our change is 3. So with an x change of 6 and a y change of 3, we've successfully found the two legs of our invisible right triangle.
Plugging those two legs into our trusty formula. 6 squared is 36, and 3 squared is 9. 36 plus 9 equals 45. Now, the square root of 45 isn't a whole number, but when we calculate it, it gives us approximately 6.71 units of distance. Just like that, you've used high-level geometry to navigate a map grid with absolute precision.
Section 5, your homework challenge.
Okay, now it's your turn to apply this structure. I highly encourage you to pause this explainer right here. Grab a pencil, get some paper, and test your precision by tackling these 5 real-world right triangle problems. Find the hypotenuse with legs of 7 and 24. Work backwards with a hypotenuse of 17. Calculate the walking distance of 9 feet east and 12 feet north. Find the map diagonal between points 2, and 6, 9. And my personal favorite, figure out the length of a ladder that leans 5 feet from a wall but reaches 13 feet high. Give it a try. Prove to yourself that you've really mastered this order.
Finally, Section 6. Education with Morality. Let's look at why the source material pairs this exact math curriculum with the Godly Learner series. They bring these concepts together, suggesting that just as discovering dependable order in math is a great tool for the intellect, relying on biblical morality brings lasting peace of mind. They present it as two sides of the exact same coin, seeking truth instead of just guessing.
The lesson argues that education without a moral compass is kind of like having powerful tools, but absolutely no direction. So the source material leaves its students with this rather provocative question to ponder. What good is it to calculate perfect physical distances with a math formula if you're still blindly guessing when it comes to the moral choices that define who you are? Thank you so much for exploring this with me today. Keep pursuing precision and keep learning.